The universe's first galaxies grew up in a frantic hurry. Entire galactic cities reached maturity in less than 1 billion years, a mere blink on the cosmic clock. This explosive growth shatters our calm ideas of how the cosmos was built. By the end of this journey, you will see how chaos, not order, is the true architect of our universe. We will uncover the violent forces, from ravenous black holes to colossal cosmic collisions, that forged everything we see. How could such a turbulent nursery of fire and fury lead to the stable galaxies of today? What does this chaotic beginning reveal about our own place in the cosmos? Are you ready to rethink everything you thought you knew about cosmic history? 400 million years after the Big Bang, the universe was a canvas of profound darkness. This was not an empty void, but a simmering sea of primordial gas, mostly hydrogen, waiting for a spark. The first flickers of light emerged from a process both violent and beautiful. Tiny ripples in the fabric of space, echoes from the universe's own explosive birth, began to pull matter together. Gravity, the master architect of the cosmos, was finally getting to work. It sculpted these slight density fluctuations into the very first structures, the cradles where stars could be born, and what stars they were. This first generation, known to astronomers as Population 3 stars, were unlike anything we see today. They were colossal behemoths, hundreds of times more massive than our Sun, burning with a ferocious intensity. Their lives were spectacularly short, ending in titanic supernova explosions that did something crucial. They forged the first heavy elements in their cores and scattered them across the cosmos, seeding the universe with the building blocks for everything to come, including planets and life itself. This era, aptly named the Cosmic Dawn, was anything but a gentle sunrise. It was a fragmented, chaotic awakening. The entire universe was also shrouded in a thick fog of neutral hydrogen gas, blocking light from traveling far. But those first brilliant stars acted as cosmic blowtorches. Their intense ultraviolet radiation began to burn away the fog, a process called reionization, slowly clearing the cosmic highways for light to travel. This was the initial state, a universe smaller, denser, and far more turbulent than our own. It was within this primordial crucible that gravity continued its relentless pull, drawing matter into the first proto-galaxies, the humble beginnings of the majestic galactic cities we see today. But gravity had a silent, invisible partner in this construction project, a mysterious force that would dictate the shape of everything to come. This invisible scaffold was the universe's most crucial construction project. While the first stars blazed brilliantly, they were merely the decoration on a framework built from something we cannot see, dark matter. Picture a vast, three-dimensional spiderweb, spun from a mysterious substance that does not interact with light at all. It is completely transparent, yet it possesses immense gravitational pull. These are the dark matter halos, and they acted as cosmic traps. Long before ordinary gas and dust could coalesce on their own, dark matter collapsed under its own gravity, forming deep wells of attraction. These wells became the gathering points, the seeds for everything that followed. Billions of them dotted the early cosmos, each a potential galaxy in the making. Ordinary matter, the stuff of stars and planets, was simply drawn into these invisible basins. The nature of dark matter itself dictated the pace of this assembly. If dark matter is what scientists call cold, meaning its particles move relatively slowly, it can clump together into smaller, denser halos very quickly. This would allow for a universe filled with many small galaxies. If it were warm, moving faster, it would smooth out the cosmos, resulting in fewer, larger galaxies forming later. The evidence we have points to a cold, dark matter universe, one that got to work building galactic foundations with astonishing speed. Without this hidden architecture, the primordial gas would have remained a formless, diffuse mist, never concentrating enough to spark a single star. The dark matter halo provided the gravitational backbone, the potential for a galaxy, but it was just an empty stadium waiting for an event. That event would be a cosmic collision, a violent merger that would ignite a firestorm of creation and truly begin the era of rapid galactic evolution. These galactic mergers were a form of cosmic chaos, a gravitational demolition derby on the grandest scale. Picture two nascent cities of stars, each billion strong, caught in an inescapable spiral. Their final collision was not a gentle union but a catastrophic upheaval. The beautiful, orderly rotation of stars and gas was violently torn apart, yet from this destruction came an incredible burst of creation. The chaotic forces of the impact funneled vast oceans of cold, primordial gas directly into the galactic cores. This gas was the raw fuel for star formation, and it was now being compressed under immense pressure, ignited by colossal shockwaves rippling through the wreckage. The result was a starburst, a firestorm of birth where stars ignited at a rate hundreds of times faster than in our placid Milky Way today. We see the brilliant afterglow of these ancient events through our most powerful eyes in the sky. The Hubble and James Webb Space Telescopes captured distant, dusty galaxies shining not in visible light, but in the intense infrared glow of billions of newborn suns, their collective heat a direct signature of a merger-induced frenzy. This violent process did more than just make stars, it sculpted the ultimate shape of the galaxy itself. The chaotic dynamics could forge a smooth, featureless elliptical galaxy or pile stars high into the central bulge of a future spiral. This was a primary engine for the universe's rapid growth, a way to convert gargantuan gas reserves into stellar mass almost overnight. But the chaos of the merger did more than just ignite a firestorm of stars. It also delivered a vast feast of gas to the darkest, most secretive resident at the very heart of the galaxy, a sleeping giant about to be woken. This sleeping giant was a supermassive black hole, and when mergers delivered it a feast of gas, it awoke with a vengeance. The result was a beacon of unimaginable power at the galaxy's core, known as a quasar. These active galactic nuclei shine with the brilliance of 1 trillion suns, making them the most luminous objects in the entire cosmos. In the early, gas-rich universe, they were far more common than they are today. As vast quantities of matter spiral into the black hole's accretion disk, they do not simply vanish. The material is compressed and heated to millions of degrees, releasing torrents of radiation across the entire electromagnetic spectrum. Often, the system also launches colossal jets of plasma, shooting out across space at nearly the speed of light. This is not just a spectacular light show, it is a force that reshapes the galaxy itself. The outpouring of energy creates a powerful feedback loop, a double-edged sword for galactic evolution. On one hand, the intense radiation and stellar winds can blast across the galaxy, heating the surrounding gas and blowing it away. This process, called quenching, can halt the formation of new stars by removing the very fuel they need to be born. It is a form of cosmic regulation, putting a hard stop on a galaxy's growth spurt. Yet, in a paradoxical twist, this same chaotic energy can also trigger new waves of star birth. Powerful outflows can slam into distant clouds of gas, compressing them so violently that they collapse under their own gravity and ignite into new suns. So the same central engine can act as both creator and destroyer, fostering life in one part of the galaxy while forbidding it in another. The discovery of incredibly bright quasars in the very early universe presents a profound puzzle. They tell us that supermassive black holes grew to billions of times the mass of our Sun with breathtaking speed, a growth spurt that challenges our understanding of physics itself. This central powerhouse introduced a new level of complexity into the galactic ecosystem, a turbulent feedback loop where chaos begets both creation and destruction. But the influence of these titans did not stay confined to their home galaxies. Their most dramatic effects were felt far beyond, on an intergalactic scale that would ultimately dictate the fate of all the cosmic structures we see today. This feedback loop created a precarious balancing act within every young galaxy. On one hand, you had the raw power of creation. When the most massive stars reached the end of their brief lives, they did not fade quietly. They detonated as supernova, blasting out titanic shockwaves that raced through the surrounding gas clouds. These stellar explosions were engines of both chaos and renewal. They seeded the galaxy with the heavy elements essential for building rocky planets and, eventually, life. Yet their immense energy could also violently push gas away, clearing out entire stellar nurseries and halting the very process of star birth they originated from. This was a self-imposed limit, a way for a galaxy to put the brakes on its own frantic growth. At the same time, the central supermassive black hole was exerting its own influence. Through its blinding radiation and jets of plasma, it could blow gigantic, heated bubbles in the intergalactic medium. This process effectively sterilized vast regions of space, raising the temperature of the galactic gas so high that it could no longer cool down, collapse, and form new stars. This is negative feedback in its most extreme form, a cosmic quenching mechanism that could starve a galaxy of its future fuel. Yet, in a stunning paradox, the very same outflows could slam into distant, colder gas reservoirs. The resulting compression could trigger a new, intense wave of star formation, a positive feedback that built new stellar neighborhoods on the outskirts of chaos. The fate of a galaxy hinged on this delicate and violent tug of war. A slight dominance of negative feedback could cause a galaxy to redden and fade, its star-forming fires extinguished billions of years ago. A better balance or a prevalence of positive triggers might lead to a galaxy like our own Milky Way, which has maintained a steady, leisurely pace of star formation for billions of years. This intricate dance explains why the early universe was not a uniform scene of frantic construction, but a mosaic of wildly different evolutionary paths. To truly understand the legacy of this chaotic period, we must learn to read the stories written in the stars themselves by analyzing the specific populations that survived from this turbulent era. These ancient stellar fossils hold the chemical memory of the universe's fiery youth. Globular clusters are vast, spherical swarms of hundreds of thousands of stars, orbiting the outskirts of galaxies like a dense cloud of ancient bees around a hive. Within their glittering cores are some of the oldest stars we have ever found, celestial elders whose composition tells a direct story of the cosmos before most galaxies even finished forming. They are pristine time capsules. The stars in these clusters are remarkably metal-poor, meaning they contain very low amounts of elements heavier than hydrogen and helium. This is because they were born from gas that had been only lightly enriched by the first few generations of supernova. They represent a second wave of stars forming from the early ashes of the first stellar giants. To create such a densely packed city of stars, the conditions had to be extreme. Astronomers theorize they were forged within the hearts of colossal, turbulent molecular clouds during periods of incredible pressure. A galaxy merger could have provided the trigger, violently compressing galactic gas and igniting a firestorm of star formation all at once, bottling up hundreds of thousands of suns in a tight gravitational knot. The sheer density of these clusters allowed them to survive for billions of years, resisting the tidal forces that would have ripped a looser group apart. Their very existence is a testament to a more violent, intense mode of star formation that was commonplace in the chaotic early universe. By studying the precise ages, motions, and chemical signatures of these stars, we can read a timeline of their host galaxies' assembly. Each cluster is a piece of the puzzle, revealing how our galaxy grew by consuming smaller galactic building blocks and their attendant clusters over cosmic time. These stellar forges represent a specific, frenzied chapter of creation, one that modern telescopes are now allowing us to read in stunning detail. The story does not end with these ancient relics, for the same chaotic processes that built the first galaxies also forged the very elements that make our world and us possible. Our cosmic timeline is being rewritten before our very eyes. The James Webb Space Telescope, with its unparalleled infrared vision, is pulling back the curtain on the universe's first act. Where the Hubble Space Telescope gave us a beautiful but hazy portrait of the early cosmos, James Webb is delivering a crystal-clear, high-definition view. It is seeing galaxies at redshifts greater than 10, meaning we are witnessing their light from a time when the universe was a mere infant, less than 500 million years old. The sheer existence of these galaxies is not the only surprise, it is their startling maturity. Some of these celestial infants appear far more massive and more structured than our best models ever allowed. They possess distinct shapes with disks and central bulges, suggesting that the chaotic processes of galactic assembly did not just begin early, they hit the ground running at a breakneck pace. This revolution is powered by more than just stunning images. James Webb's spectroscopic instruments dissect the light from these ancient objects, confirming their vast distances and revealing their chemical fingerprints. In galaxies that should, by all rights, be composed of nothing but primordial hydrogen and helium, astronomers are finding the distinct signatures of heavier elements like oxygen and carbon. These elements are the ash from earlier stellar furnaces, meaning that entire generations of stars must have already lived, died, and enriched the cosmos in an astonishingly short period. This discovery strikes at the heart of the long-held hierarchical model of galaxy formation, the idea that small galaxies slowly merged over billions of years to build large ones. The new data suggests a cosmos where immense structures formed with breathtaking efficiency, demanding more violent and potent formation mechanisms than we had ever conceived. Every new data transmission from James Webb is a flood of cosmic puzzles. Each deep field image, each spectrum of a primordial galaxy, holds a potential clue that could rearrange our understanding of the universe's chaotic youth. We are no longer just theorizing about those initial bursts of star formation or the first awakenings of supermassive black holes. We are gathering the direct, empirical evidence to put our ideas to the test. This observational revolution is forcing us to look back at those ancient engines of chaos, the mergers and the feedback loops, and ask if they were even more powerful and potent than we dared to believe. The telescope's findings are not just filling in gaps in our knowledge, they are revealing an entirely new narrative for how our universe built its grandest structures. This long-standing idea of cosmic construction now faces a profound challenge. For decades, the hierarchical model has been a pillar of cosmology, painting a picture of a universe built patiently from the bottom up. Small clumps of dark matter and their attendant gas would slowly merge like cosmic Legos, assembling larger and larger structures over billions of years. It is an elegant, logical progression, yet the vision from our newest telescopes reveals something far more dramatic. we are finding galaxies of immense size and stunning maturity existing at the very dawn of time, celestial giants that seemingly grew up overnight. This suggests the early cosmos was not always a place of gradual assembly. In the denser, more intense environment just after the cosmic dawn, gravity could work in overdrive. Within vast, overdense regions known as Proto-Clusters, the enhanced gravitational pull could have triggered a rapid, almost monolithic collapse. Instead of a slow dance of mergers, entire galaxies might have condensed directly from massive pools of gas in a top-down fashion, reaching maturity in a single, frantic burst. This does not mean we discard the hierarchical model entirely. Rather, we must refine it, recognizing that the early universe permitted multiple, parallel pathways to galactic adulthood. Gravity was not a patient foreman overseeing a single blueprint, but the conductor of a chaotic symphony, allowing for both slow, steady construction and sudden, explosive growth. The true picture of galaxy formation is becoming one of immense complexity, where the simple rules of gravitational attraction played out in an environment so rich with possibility that the results were anything but simple. This revised understanding forces us to look beyond the galaxies themselves, to the vast, invisible rivers of fuel that connected them all, a structure known as the cosmic web. While the chaos of mergers and black holes raged within galaxies, a quieter, more constant nourishment flowed from the cosmos itself. Vast cosmic aqueducts composed of pristine hydrogen and helium streamed along the invisible filaments of the dark matter web. This was cold flow accretion, a fundamental process where gas, never heated to extreme temperatures, slid directly into the gravitational wells of young galaxies. Think of it not as a violent collision, but as a continuous, cold river of fuel flowing into a galactic reservoir. Unlike the superheated gas that glows brightly and resists collapse, this cold, primordial material was ready to form stars almost immediately upon arrival. It provided a steady, efficient food source that could power intense starbursts for hundreds of millions of years. In the early universe, before supermassive black holes grew powerful enough to blow gas away, this was likely the primary way galaxies fed their frantic growth. Supercomputer simulations of the early cosmos reveal this beautiful, intricate structure. They show delicate tendrils of gas tracing the dark matter scaffolding, funneling fresh material from the vast intergalactic emptiness directly into the dense, hungry cores of proto-galaxies. This constant inflow solves a critical puzzle. How could a galaxy sustain such a ferocious rate of star formation without quickly burning through all its available fuel? The answer lies in these cosmic rivers, which provided a continuous external supply, topping up the galactic gas tank even as it was being rapidly consumed. This smooth, cold accretion worked in tandem with the violent, merger-driven growth. One process was a steady drip feed, the other a catastrophic feast. Together, they created a dynamic and unpredictable environment, where a galaxy's evolutionary path was shaped by the balance between gentle inflow and chaotic collision. The legacy of these ancient rivers of gas is written in the stars themselves, but to read it, we must learn to listen to the subtle language of galactic light. Our universe began with a chemical blank slate composed of nothing but hydrogen, helium, and a trace of lithium. From this pristine simplicity, the very first stars were born, colossal titans known as Population 3. Their formation was a fundamental departure from anything that follows today. Without the dust and heavier elements that help modern gas clouds cool and fragment, these primordial clouds could only collapse into truly massive structures. The result was stars of almost unimaginable scale, each 100s of times more massive than our own sun. Their lives were as brilliant as they were brief. Powered by immense gravity, they burned their nuclear fuel at a furious, unsustainable rate, shining with a ferocious ultraviolet light that helped pierce the cosmic dark ages. Their deaths were even more consequential. For the very largest of these giants, their final moments were not just an explosion but a complete self-annihilation. In a cataclysm known as a pair-instability supernova, the core became so hot that it spontaneously created matter and antimatter pairs, triggering a runaway reaction that utterly obliterated the star, leaving no remnant behind. It was a total conversion of mass into pure, universe-shaking energy. Slightly smaller, yet still immense, population 3 stars met their end in colossal core collapse supernova. It was within these unimaginable pressures and temperatures that the universe forged its first heavy elements. In a few fleeting moments, the violent alchemy of these explosions synthesized entirely new kinds of matter, creating the first carbon, the first oxygen, and the first iron. This was the cosmos's first act of pollution, a beautiful contamination that would change everything. These newly forged elements were then blasted outward at incredible speeds, seeding the surrounding primordial gas with the essential ingredients for everything to come. This initial chemical enrichment was a pivotal turning point. For the first time, the universe's gas was no longer pristine. The presence of even tiny amounts of these metals, as astronomers call all elements heavier than helium, had a profound cooling effect. This allowed gas clouds to fragment more efficiently, collapsing not into single behemoths, but into hundreds of smaller, more stable stars. The era of the monstrous population 3 stars was over, giving way to the longer-lived population 2 stars, the ancient stellar fossils we still observe today in globular clusters. The feedback from these first supernovae was a double-edged sword. Their shockwaves could violently reheat and disperse gas in small dark matter halos, effectively shutting down star formation in those fragile environments. Yet in larger halos, those same shockwaves could slam into adjacent gas clouds, compressing them and triggering the very next wave of stellar birth. The legacy of these first stars is therefore written in the chemical fingerprints of the oldest stars we can now observe. Their metal-poor compositions a direct record of that first explosive chapter. While we have never directly seen a population 3 star, their existence set the entire chemical and dynamical stage for the cosmos, initiating the complex cycles of matter that would eventually build worlds like our own. Galaxies are not isolated islands, but dynamic engines that breathe. Within their spiral arms, the life cycle of stars drives a continuous exchange of matter with the vast space beyond. When massive stars reach the end of their lives, they detonate as supernova, and even during their lives, they blast out powerful stellar winds. These events collectively act like a piston, launching fountains of hot, metal-enriched gas high above the serene disk of the galaxy. This gas, now carrying the heavy elements forged in stellar cores, rises into the galactic halo where it can cool and condense into massive, dense clouds. Eventually, pulled back by the galaxy's gravity, this material rains down upon the disk like a cosmic downpour, seeding pristine regions with the essential ingredients for rocky planets and ultimately life. This beautiful cycle of fountain and rain ensures that the products of one stellar generation become the building blocks for the next. But sometimes the galaxy's engine breathes out with too much force. In galaxies undergoing ferocious starbursts or those powered by incredibly active supermassive black holes, these outflows can become permanent ejections. They transform into galactic winds, blasting material away at thousands of kilometers per second, fast enough to escape the galaxy's gravitational pull entirely. This is a process of mass loss, and its consequences are profound. By violently expelling the very gas that forms stars, these winds can effectively quench a galaxy's future star formation, halting its growth in its tracks. The efficiency of this process created a critical feedback loop. In smaller galaxies with weaker gravity, even modest stellar activity could drive powerful winds, stripping them of fuel and limiting their final size. In contrast, the immense gravity of a massive galaxy could hold onto its gas more tenaciously, allowing for a longer, more complex evolutionary history. This is one reason we see such a diversity of galaxy types in the universe today. The material blown out by these winds does not simply vanish. It travels far, enriching the vast, empty spaces between galaxies with heavy elements. The intergalactic medium, once a pristine sea of hydrogen and helium, became subtly polluted with the ashes of countless stellar furnaces. This means that the very fabric of deep space carries a chemical memory of ancient galactic turmoil. Observing these winds in distant, young galaxies is a primary goal for our most advanced observatories, as they are a direct, real-time manifestation of the violent feedback that shaped the cosmos. This continuous, large-scale cycling of matter reveals a universe deeply interconnected, where every galaxy's growth and eventual fate is tied to its ability to manage its own turbulent energy. A billion years feels like an eternity from our human perspective, but for the first galaxies, it was a single, frantic developmental sprint. The entire cosmic environment was primed for speed. The universe was vastly denser then, a crowded neighborhood where galaxies lived in close quarters. This density fundamentally accelerated the clockwork of gravity. The process of dynamical friction, which slowly causes orbiting objects like small galaxies to lose energy and spiral inward, happened at a dramatically faster pace. What might take billions of years in our sparse modern universe could unfold in just a few 100 million years back then. Collisions and mergers were not rare, drawn-out events. They were the standard, rapid-fire method of construction. This was paired with an almost limitless supply of fuel. The gas reservoirs were colossal, vast oceans of pristine hydrogen and helium that had not yet been churned and heated by countless supernovae. This purity meant the gas could cool with supreme efficiency and collapse directly into stars, converting matter into suns at a rate that would be unimaginable in a modern galaxy like our own. Even the yardstick we use to measure cosmic time, the Hubble time, was radically different. When the universe was only 1 billion years old, that was its entire history. Galaxies had to accomplish in that brief window what their modern counterparts have taken over 13 billion years to achieve. This compression of every single timescale created a perfect storm for growth, an era where slow and steady lost the race. The frantic, almost rushed maturity we see in these ancient galaxies is not a puzzle. It is the direct result of a cosmos operating on fast forward. This realization forces a profound shift in our perspective, compelling us to ask where the most extreme examples of this rapid growth occurred and what they can teach us about the ultimate limits of cosmic construction. The most extreme galactic evolution occurred in the universe's bustling metropolises. These were the Proto-Clusters, the precursors to the colossal galaxy clusters we see today. Within these dense cosmic neighborhoods, the very rules of galaxy formation were rewritten by the sheer intensity of the environment. Picture a region where dark matter halos were packed so tightly together that their gravitational influence created a frenzied, miniature cosmos all its own. This was not the average sparse galactic field. This was a galactic accelerator, a pressure cooker for celestial development. In these crowded quarters, mergers were not just frequent, they were nearly constant. Galaxies did not have the space for a quiet, solitary existence. They were perpetually nudged and pulled by their neighbors' gravity, locked in a relentless dance of interaction. These gravitational tidal forces could strip away a galaxy's outer gas, warp its structure, and efficiently funnel vast reserves of cold gas directly into its core. The result was a different evolutionary pathway altogether. While an isolated galaxy might slowly accrete gas and form stars at a leisurely pace, a galaxy in a proto-cluster was forced to grow up fast, often maturing into a massive, red and dead elliptical galaxy billions of years before its isolated cousins. The scale of the activity was breathtaking. A single gravitational event could trigger intense, simultaneous starbursts across dozens of galaxies at once. Imagine not just one galaxy igniting in a firestorm of creation, but an entire district of them lighting up in a coordinated cosmic firework display. This collective frenzy had a lasting impact on the space between the galaxies as well. The intracluster medium, the thin, superheated gas that fills a cluster, was forged in this era. It was warmed early on by the sheer violence of gravitational collapse as the proto-cluster formed, and then superheated by a dense population of active black holes and countless supernovae, their combined feedback blowing out and enriching the shared environment. Today, our most powerful observatories are pinpointing these ancient cradles of giants. The James Webb Space Telescope and the ALMA radio array are identifying proto-clusters at record-breaking distances, seeing them as they were when the universe was a mere fraction of its current age. The stunning discovery that some of the very first known galaxies already resided in such dense environments is a profound clue. It tells us that a galaxy's cosmic address, its location within the grand filamentary web of the universe, was perhaps the single greatest factor in determining its destiny. The chaotic processes that governed all early galaxies were amplified here to their absolute extreme, creating the universe's first celestial titans in a frantic, spectacular rush. The early cosmos was a gallery of beautiful monstrosities. When we look at the deep field images from the James Webb Space Telescope, we do not find the elegant spirals of our modern night sky. Instead, we see a chaotic menagerie of shapes, galaxies that look like glowing train wrecks, fragmented pearls, or lopsided blobs of light. This peculiar morphology is not a sign of failure, but a direct signature of a universe still under construction. These galaxies were fundamentally different from our own, drowning in vast oceans of cold, primordial gas. Within these turbulent systems, gravity worked on an epic scale, pulling together giant, unstable clumps of gas and young stars. Each of these clumps was a stellar nursery in its own right, containing the mass of millions of suns. They were not fixed in place, but roamed the young galaxy like celestial icebergs, drifting, interacting, and sometimes merging in a slow, gravitational dance. Over time, their orbits would decay, and they would spiral inward, sinking toward the galactic center to deliver their immense mass and help forge the central bulge we see in so many mature galaxies. This entire process was constantly fueled and disrupted by the violent environment. High-speed rivers of fresh gas flowing in from the cosmic web would slam into the galactic disk, stirring up the material and preventing the formation of a stable, rotating structure. Meanwhile, the very stars being born within these clumps contributed to the chaos. The most massive ones lived fast and died young, exploding as supernovae. Their collective energy could blow gigantic, blistering holes in the galactic gas disk, further shattering any semblance of order. This clump cluster phase is now understood not as an anomaly, but as a fundamental, almost universal, stage of growth for massive galaxies. It represents a period of intense internal evolution, where the galaxy is literally building itself from the inside out through the migration and merging of its own colossal components. The transition from this disordered, clumpy infant to a sleek, mature spiral is one of the most profound transformations in cosmic history. We are now witnessing this very transition across billions of years, watching as the foundational chaos of the early universe gradually gives way to the majestic structures we recognize today. This invisible magnetic tapestry was woven into the chaos from the very beginning. While gravity pulled matter together on the grandest scales, a subtler force was at work within the swirling gas clouds, guiding and resisting the flow. Interstellar magnetic fields, though unimaginably faint at first, became the hidden architecture within the storm. They were likely born from the faintest seed fields, perhaps generated by the first stars and their explosive deaths, and then dramatically amplified by a natural cosmic process. As turbulent gas swirled and churned within young proto-galaxies, it acted like a colossal dynamo, twisting and stretching these magnetic lines of force, strengthening them over millions of years until they became a tangible presence. The influence of these fields was profound, acting as a regulatory force on the frantic pace of star formation. Within a dense molecular cloud on the verge of collapse, gravity pulls everything inward. But magnetic fields create a form of pressure, a supportive cushion that can prop up a cloud against its own weight, slowing or even preventing its fragmentation into stars. They channel the flow of ionized gas, directing it along invisible rails and preventing it from freely collapsing. This magnetic support helps explain why star formation in the modern universe is so inefficient, with only a tiny fraction of a cloud's gas ever turning into stars. In the early cosmos, as these fields were still building their strength, their evolving influence may have been a key factor in modulating the incredible starbursts. They also played a crucial role in the most violent events. The colossal jets erupting from active supermassive black holes are tightly focused and propelled across vast distances by powerful magnetic fields wound up in the accretion disk. Without this magnetic guidance, those outflows would be formless explosions, not the precise galaxy-shaping engines they became. We are only beginning to map this invisible component of cosmic evolution. The strength and configuration of these primordial magnetic fields remain one of astronomy's great mysteries. How did they grow from negligible strengths to the microgauss values we measure in galaxies today? The answer lies in that turbulent dynamo action, a process we can now simulate in supercomputers, watching as virtual galaxies braid magnetic fields into their very structure. This magnetic layer adds a beautiful complexity to our models. It means the early universe was not just a contest of gravity and pressure, but a dance that included this invisible third partner, a force that could gently steer the currents of gas, regulate the birth of suns, and ultimately help write the destiny of the first galaxies. This intricate web of physics, with magnetism as a key thread, reveals a system of even greater sophistication than we first imagined. Yet for all this complexity, the ultimate legacy of the early universe is written in the sky above us today, in the stunning diversity of galactic forms that have endured for billions of years. This pervasive hydrogen fog was the final veil over the newborn cosmos. For hundreds of millions of years, the universe was an opaque realm, its light trapped and absorbed by a dense, neutral gas. The transformation began within the chaotic furnaces of the first galaxies. As massive stars ignited and quasars flared to life, they bombarded this fog with an unrelenting barrage of ultraviolet radiation. Each photon was like a microscopic blowtorch, striking a hydrogen atom and stripping away its electron, turning the neutral gas into a transparent, ionized plasma. This was the Epoch of Reionization, a cosmic sea change where the universe went from being shrouded to clear. The process was neither quick nor uniform. It was a patchwork of clearing, like holes burning through a vast blanket, gradually growing and merging until the entire cosmic fabric was transparent. The success of this great unveiling hinged on a delicate escape act. the ionizing photons born in stellar nurseries and accretion disks had to flee their host galaxies without being absorbed by the very gas that filled them. In a galaxy choked with dense, turbulent gas, most of this light was trapped, its energy wasted on heating local clouds. But in systems where supernova winds and black hole jets had already blown away the cobwebs, carving clear bubbles and channels through the interstellar medium, the ultraviolet radiation could stream out unimpeded. These galaxies became the efficient beacons of reionization, their light punching through the gloom to burn away the cosmic fog on an intergalactic scale. Once the process was complete, the universe itself was fundamentally altered. The intergalactic medium was now a hot plasma, heated to tens of thousands of degrees. This created a powerful form of cosmic feedback. For the small, fledgling galaxies that formed later, this hot environment posed a serious challenge. Their weak gravitational pull could no longer easily draw in and cool the now hot gas, effectively stifling their growth before it could even properly begin. Reionization had raised the floor for galaxy formation, setting a minimum mass for survival and forever shaping the population of galaxies that would follow. The local, chaotic processes within individual galaxies, the starbursts, the feedback, the clearing of gas, had collectively orchestrated a change to the universe itself, demonstrating how intimately the small scale and the cosmic scale are woven together. A profound mystery lurks right in our own galactic neighborhood. Our most sophisticated computer models of cosmic evolution paint a very specific picture. They tell us that thousands of small, dark matter clumps should be orbiting our Milky Way, the leftover building blocks from its assembly. Yet when we look up at the sky, we count only a few dozen small, faint satellite galaxies. The vast majority of these predicted structures are simply missing. This cosmic case of the missing companions is one of astronomy's most persistent puzzles. Where did all those dark matter halos go? The answer may be written in the violent conditions of the early cosmos. In that first billion years, the universe was flooded with a harsh, relentless glare of ultraviolet radiation. This was the final, sterilizing act of reionization. For the smallest, most fragile dark matter halos, this radiation was a death sentence. Their gravitational grip was too weak to hold onto gas that was being heated to extreme temperatures. Without the ability to cool down and condense, these potential galaxies were starved of the fuel needed to light up. They became dark, ghostly halos, filled with invisible matter but devoid of stars, forever lost to our telescopes. But radiation was not the only destructive force. Inside those few small halos that did manage to form some of the first stars, another kind of chaos unfolded. When those massive stars reached the end of their brief lives, they exploded. In a large galaxy, such supernova feedback is a regulating force, but within a tiny proto-galaxy, it was a cataclysm. The collective blasts from just a handful of stars could generate enough energy to blow the entire gas reservoir clear out of the halo's feeble gravitational grasp. These systems effectively blew themselves apart, ejecting their future and stunting their growth in a single, self-inflicted burst. This means the satellite galaxies we see orbiting the Milky Way today are the rare survivors, the lucky few that were either massive enough to withstand the early turmoil or that formed just after the most intense period of radiation had passed. Their very existence is a direct consequence of the chaotic feedback loops established at the dawn of time. The frantic growth of the first giant galaxies and their brilliant quasars did not just shape their own destinies. They set the rules for everyone else, effectively deciding which small structures would ever get a chance to shine. This deep connection ties the most distant, ancient events directly to the present-day anatomy of our own home galaxy. revealing how the universe's fiery beginnings dictated the sparse, quiet cosmic neighborhood we inhabit today. These digital universes run on some of the most powerful supercomputers on Earth, translating fundamental physics into a virtual cosmos. Through monumental simulations like Illustris and Eagle, astrophysicists can witness the entire saga of cosmic structure unfold from the first flickers of light to the modern era. The codes are staggeringly complex, weaving together the laws of gravity, the fluid dynamics of gas, the explosive feedback from supernova, and the colossal energy output from supermassive black holes. This is not a simple animation. It is a self-consistent digital laboratory where millions of galaxies are born, evolve, and interact according to our best understanding of physical law. We can watch in accelerated time as dark matter halos, the invisible scaffolding of the universe, gravitationally attract one another and merge. We see vast rivers of cold gas flow along the cosmic web, feeding the hungry proto-galaxies at their intersections. The simulations then capture the inevitable chaos, as galactic collisions trigger firestorms of star formation and central black holes awaken, blasting out energy that can either quench a galaxy or spark new life within it. This virtual reality allows us to run experiments on a scale that is otherwise impossible, testing how different recipes of physics lead to the diverse galactic zoo we observe. The true power of these simulations is revealed when they produce a universe that looks remarkably like our own. When the statistical distribution of galaxy masses, shapes, and star formation rates from a simulation matches the data from our telescopes, it gives us profound confidence that we are on the right track. We are capturing the essential story, but the opposite result is equally valuable. The recent James Webb observations of unexpectedly massive and mature infant galaxies present a direct challenge to many existing simulations. The digital universes often struggle to grow such giants so quickly. This failure is not a defeat, it is a crucial clue. It tells us our models are missing a vital ingredient, perhaps a more efficient mode of star formation, a faster way to feed black holes, or a previously overlooked channel for gas accretion. This continuous, dynamic dialogue between the predictions of our digital cosmos and the raw data from our telescopes is the engine of modern astrophysics. It forces us to refine our theories, to add new layers of complexity, and to ultimately develop a deeper, more truthful narrative of how chaos forged the first galaxies. The stars in our own galactic backyard are ancient scribes, holding chemical records of a time long before the Earth existed. This field of study, galactic archaeology, allows us to read the elemental composition of a star like a page from a cosmic history book. Each star preserves, with remarkable fidelity, the exact chemical makeup of the interstellar gas cloud from which it condensed. By analyzing the light from the oldest stars in the Milky Way, we can measure the precise amounts of elements like iron, oxygen, and magnesium they contain. These ratios are the critical clues. A star showing a high abundance of what astronomers call alpha elements, such as oxygen and magnesium, relative to its iron content, tells a very specific story. It points to a rapid formation from gas that was enriched almost exclusively by core collapse supernova, the violent deaths of short-lived, massive stars. This is the chemical signature of a frantic, intense starburst, the kind that rocked the early, chaotic universe. In contrast, a different chemical pattern, one richer in iron, suggests a later birth. Iron is forged over longer timescales in the explosions of white dwarf stars, indicating a more settled galactic environment. This chemical tagging lets us do more than just date stars. It allows us to trace their origin. We can now identify entire streams of stars orbiting our galaxy that share a distinct chemical fingerprint, different from their surroundings. These are the ghostly remains of smaller galaxies that were torn apart and consumed by the growing Milky Way billions of years ago. Each stellar stream is a fossil of an ancient merger, a direct piece of evidence for our galaxy's violent and piecemeal assembly. This technique provides a powerful, ground truth complement to peering at distant, young galaxies. While telescopes like James Webb show us the chaotic construction sites of the early universe, galactic archaeology lets us examine the local, finished products of that same era. The chemical fingerprints we measure in the oldest stars are the direct, tangible legacy of that frantic nucleosynthesis within the first galaxies, a permanent record of the chaos that built our cosmic home. The serene spiral galaxy is heading for a cosmic wrecking yard. As it drifts toward the immense gravity of a galaxy cluster, it encounters an invisible, superheated wind. This is the intracluster medium, a plasma of gas so hot it glows in X-rays. For the galaxy, this plasma acts like a hurricane force gale. The phenomenon is called ram pressure stripping, and it is brutally efficient. The tenuous gas spread throughout the galaxy's disk offers little resistance. As the galaxy plows through this hostile environment at millions of kilometers per hour, the interstellar gas is simply ripped away like dust blown from an old book by a sudden gust. This is not a gentle loss, it is a violent, systematic removal of the galaxy's future. The cold, dense molecular clouds, the very nurseries where new stars are born, are torn from their gravitational anchors and scattered into the void. Without this raw material, the galaxy's star-forming machinery grinds to a halt. Its spiral arms, once glowing with the blue light of young, massive stars, begin to dim. But the assault does not end there. Within the crowded cluster, close encounters are constant. In a process known as gravitational harassment, the galaxy experiences repeated, high-speed flybys from its neighbors. These are not slow, merging dances, but swift, disruptive passes. Each gravitational tug can warp the galaxy's delicate shape, pull stars into long tidal streams, and further shake loose any remaining pockets of gas that ram pressure might have missed. The galaxy is being systematically dismantled by its environment. This transition from a vibrant, blue, star-forming spiral to a passive, red, and aging elliptical is one of the most dramatic transformations in the universe. It represents a different kind of chaos altogether. This is not the internal chaos of supernova feedback or a central black hole, but an externally imposed order, a brutal regulation enforced by the galaxy's own cosmic address. The cluster itself acts as a galactic graveyard, where the vibrant fires of creation are methodically extinguished. This environmental quenching completes the picture of galactic evolution, proving that a galaxy's destiny is forged by a constant dialogue between the storms raging within and the immense pressures applied from without. The astronomical frontier is now a race against time itself, pushing deeper into the cosmic past than we ever thought possible. This journey hinges on a single, powerful number known as redshift, symbolized by the letter Z. It is not just a measure of distance, but a direct window into look-back time. The higher the redshift, the further back we peer into the universe's infancy. Our current champion in this quest, the James Webb Space Telescope, has already identified stunning galaxy candidates at redshifts beyond 14. We are witnessing their light from a period when the cosmos was a mere 280 million years old, a time so ancient it defies easy comprehension. Yet spotting these faint smudges of light is only the first step. The true challenge lies in confirmation. Astronomers must perform meticulous spectroscopic follow-up, carefully dissecting that incredibly faint light to analyze its chemical fingerprints and confirm its staggering distance. This is painstaking work at the very edge of detection, the pursuit does not end with Webb. A new generation of observatories stands ready to push the frontier even further. The Nancy Grace Roman Space Telescope, with its incredibly wide field of view, will conduct vast surveys of the sky, spotting thousands of these primordial gems for deeper study. Meanwhile, on the ground, the extremely large telescope will use its colossal, 39-meter-wide mirror to gather unprecedented amounts of light, potentially allowing us to see the first individual stars. This is the ultimate goal, to directly witness the era of the mythical population 3 stars, the very first stellar giants whose fiery lives and explosive deaths set the entire cosmic story in motion. Every step back in time brings a new surprise, a new galaxy that seems too massive or too mature for our best models to explain. These are not mere record-breaking curiosities. They are the initial conditions of the cosmos, the foundational seeds from which all subsequent structure, including our own galaxy, ultimately grew. This relentless push to higher redshifts is our only chance to directly witness the chaotic, messy birth of galaxies and finally understand the very first moments of their existence. Within the colossal gas clouds that served as stellar nurseries, a hidden storm was always raging. This was not a simple, smooth flow of material, but a churning, supersonic chaos of swirling eddies and violent shockwaves. We call this interstellar turbulence, and in the early universe, it was the relentless heartbeat of a galaxy's life cycle. This turbulence was driven by the most violent events the cosmos could offer. The shockwaves from supernova explosions would rip through the gas, sending it spinning into wild vortices. Galactic mergers would stir the interstellar medium like a giant spoon, and the high-speed inflow of fresh gas from the cosmic web created a constant, buffeting wind. This chaotic motion played a profoundly dual role in the story of star birth. On one hand, all that churning energy created a form of internal pressure, a kinetic support that could prop up a giant molecular cloud against the relentless pull of its own gravity. It could prevent the cloud from collapsing, effectively putting a temporary halt on the formation of new stars. Yet, in a beautiful paradox, that same turbulence was also the essential trigger for creation. Wherever these chaotic flows collided, they created immensely dense regions, compressed pockets of gas squeezed in the shock fronts between colliding streams. It was within these turbulent seeds that gravity could finally get a decisive grip, pulling the densest knots together until they ignited into brilliant, newborn star clusters. The entire process hinged on a delicate balance, a cosmic tug of war between the dissipating energy of the turbulence and the gathering power of gravity. The outcome of this contest determined a galaxy's star formation efficiency, the rate at which it could transform its raw gaseous fuel into shining suns. In the frantic early galaxies where turbulence was driven to extreme levels, this efficiency was both high and wildly unpredictable. Star formation did not proceed as a steady trickle, but in violent, episodic bursts. A galaxy could witness a ferocious firestorm of stellar birth, only for the resulting supernova to inject so much turbulent energy back into the system that the next wave of star formation was delayed for millions of years. This microscopic chaos within the gas is the critical link, the physical mechanism that directly translates the large-scale violence of galactic collisions and quasar outbursts into the very specific pattern of star formation we observe. To truly model the frantic growth of the first galaxies, we must first learn to read the language of this primordial interstellar storm. Our foundational picture of dark matter might be incomplete. For decades, the leading model has described it as cold, a slow-moving substance that clumps together easily to form the gravitational seeds for galaxies. This idea has been incredibly successful at explaining the large-scale cosmic web we observe, yet when we zoom into the smallest scales, puzzles emerge. The most famous is the missing satellites problem, where our telescopes find only a handful of small galaxies around the Milky Way, while simulations predict thousands. This discrepancy has prompted physicists to ask a radical question. What if dark matter is not entirely cold? A warm dark matter model proposes that these particles moved with significant speed in the early universe. This slight increase in velocity would have a dramatic effect, smoothing out the smallest ripples in the dark matter fabric. It would prevent the countless tiny dark matter clumps from ever forming, naturally explaining the scarcity of small satellite galaxies we actually see. This is not the only alternative. Another compelling idea is that dark matter particles might interact with each other or with normal matter through some force beyond gravity. If dark matter has even a tiny capacity for self-interaction, it could solve another puzzle, the cusp core problem. Simulations often predict dense, sharp peaks of dark matter at the centers of galaxies, but observations of many dwarf galaxies suggest their cores are softer and more spread out. If dark matter particles can collide and scatter, they would effectively smooth out these central cusps into shallower cores, bringing our theoretical predictions into better alignment with real-world data. The true nature of this invisible cosmic scaffolding remains one of the most profound mysteries in all of science. It is a question that reaches far beyond particle physics, directly into the heart of our story. The specific properties of dark matter set the initial conditions for all the chaos that followed. They determined how quickly the first structures could collapse, how many small building blocks were available for mergers, and ultimately, the very timeline of galactic growth. If dark matter is more complex than our standard cold model, it would mean we must revise our understanding of the universe's chaotic infancy, the frantic pace of the early cosmos, the violent dances of merging galaxies, and the brilliant ignition of the first quasars were all choreographed by the invisible hand of dark matter. To finally grasp its true identity is to unlock the first and most crucial chapter in the epic of how our universe was built. This stunning variety in the galactic zoo is the final, beautiful testament to a chaotic beginning. From the elegant whirl of a spiral to the smooth, golden glow of an elliptical, every galaxy's form is a unique life story written by the specific chaos it endured. There is no single cosmic assembly line, only a vast spectrum of individual journeys. A galaxy's destiny was shaped by a random roll of the dice across multiple factors. Its final form is the product of its unique merger history, the rhythm of its gas accretion, the precise timing of its supernova feedback, and the influence of its galactic neighborhood. A series of violent major mergers will likely tear apart any delicate disk, scrambling the stars into a smooth, ellipsoidal swarm. In contrast, a quieter existence, marked by a steady, gentle inflow of cold gas, allows for the peaceful cultivation of a vast, rotating spiral disk. Even a seemingly minor initial condition, like the original spin of the invisible dark matter halo, could set a galaxy on a completely different path, determining whether a stable disk could form and persist for billions of years. This explains why two galaxies with nearly identical masses can look and behave so differently today. Their evolutionary stories diverged based on their personal experiences with cosmic violence and fortune. Much like two individuals with similar potential can lead entirely different lives shaped by their unique environments and choices. This lack of a single, deterministic outcome is the hallmark of a truly complex system. To understand the universe, then, we are not searching for one grand, unified story of galaxy evolution. We are instead learning to read a near-infinite library of individual biographies, each one governed by the same fundamental laws of physics, but each one telling a story that is entirely its own. A new golden age of cosmic archaeology is unfolding right here in our own galactic home. The European Space Agency's Gaia mission is at the forefront of this revolution, performing the most detailed census of the Milky Way ever attempted. It is precisely charting the positions, motions, distances, and even the chemical compositions of over 1 billion stars, transforming a static picture of our galaxy into a dynamic, three-dimensional movie. This immense and ever-growing dataset is like a digital time machine, allowing us to rewind the motions of stars and uncover the ghostly signatures of our galaxy's violent youth. We can now see with stunning clarity the stellar streams that wrap around the Milky Way, the torn apart remains of smaller galaxies that were gravitationally shredded and consumed. These streams, often whimsically named after rivers or mythological figures, look like cosmic spaghetti tangled throughout our galactic halo. Each one is a distinct fossil, a relic of a separate accretion event. By analyzing the collective motion and the chemical fingerprints of the stars within a stream, astronomers can perform a kind of celestial autopsy. They can determine when the merger happened, what the original galaxy was like, and how its assimilation forever altered the Milky Way's own structure and stellar population. One of the most significant events uncovered by this data is the ancient collision with a galaxy now called Gaia Enceladus Sausage. This major merger, which occurred around 10 billion years ago, was a defining moment for our galaxy. The impact fundamentally reshaped the early Milky Way, likely contributing a vast number of stars to our galactic halo and thickening its disk. It was a violent, chaotic episode that helped forge the galaxy we recognize today. This local archaeological dig provides an irreplaceable laboratory. While we can only see distant, young galaxies as faint smudges of light, we can resolve individual stars within the Milky Way. We can study the intricate details of galactic mergers and their aftermath right on our cosmic doorstep, providing a resolvable, nearby model for the very same processes that built all massive galaxies in the early universe. The serene spiral we see arching across the night sky is a beautiful illusion, masking a history written in collisions. Our own galactic story is one of assembly through chaos, a profound link between the quiet present and the tumultuous dawn of cosmic time. Our entire cosmic census comes with a fundamental blind spot. We are observing the universe from a single, fixed address, and this limits our perspective in a profound way. The deepest images from the James Webb Space Telescope, like the celebrated deep fields, are not panoramic views of the entire infant cosmos. They are more like core samples, narrow drill holes into the fabric of space-time that reveal a tiny, specific column of the ancient universe. The patch of sky we happen to be studying might be a bustling galactic metropolis, a region of unusually high density where gravity worked with exceptional speed. Alternatively, our most powerful telescopes might be pointed at a cosmic backwater, a quiet void where galaxy formation proceeded at a more leisurely pace. This inherent uncertainty is known as cosmic variance, a statistical limitation that arises because we can only observe from one location. It means the properties we measure for the earliest galaxies, such as their average mass or how densely they were packed together, come with a built-in margin of error. The surprising maturity of some early galaxies might not completely shatter our theories, but could instead reflect the unique character of our particular cosmic sample. This is not a flaw in the data, but a reminder of the sheer scale we are dealing with. We are trying to understand the entire universe by studying a handful of snapshots from its earliest photo album. The solution lies in expanding our view. Future missions like the Nancy Grace Roman Space Telescope are designed as wide-field surveyors. They will map enormous volumes of the high redshift universe, effectively turning our narrow core samples into a vast geological survey. This will allow us to compare thousands of different cosmic neighborhoods, finally understanding the full range of environments in which galaxies were born. Cosmic variance teaches us a crucial lesson in scientific humility. The chaotic processes we observe were not uniform, and our singular viewpoint on Earth offers only one chapter in a story of incredible diversity. Theoretical models are not static decrees, but living ideas that must prove their worth against the hard light of reality. A cosmologist might spend years building a sophisticated simulation of galactic growth, weaving the known laws of gravity and hydrodynamics into a digital universe that predicts how gas should flow and stars should ignite. This virtual cosmos, born entirely from mathematics and code, makes a specific forecast. It tells observers exactly what to look for with our most powerful telescopes. Perhaps it predicts the faint, telltale signature of cold hydrogen gas streaming along the cosmic web, a process known as cold flow accretion. Armed with this prediction, astronomers then point an instrument like the James Webb Space Telescope at a patch of sky, collecting photons that have traveled for over 13 billion years. They dissect this ancient light with a spectrograph, searching for the specific fingerprint of that inflowing gas. The moment of truth arrives when the data is processed. Sometimes the observation is a stunning confirmation, a perfect match that validates the theoretical framework. At other times, the universe delivers a profound surprise. The data reveals a galaxy that is far too massive, too structured, or too mature to exist within the model's timeline. This is not a failure of science, but its very engine. A contradiction is a catalyst. It forces theorists back to their digital drawing boards. They must ask difficult questions. Do we need to enhance the role of supermassive black hole feedback, making it even more potent at triggering star formation? Could an alternative form of dark matter, perhaps warm or self-interacting, explain the rapid assembly, or is an entirely new mechanism for galactic growth required, one we have not yet even conceived? This refined theory then makes a new set of predictions which are handed back to the observers, who design new experiments and build even more sensitive instruments to test them. This beautiful, iterative dance between the abstract world of theory and the tangible world of observation is how cosmology progresses. We are currently living through a golden age of this dialogue, where the fire hose of new data from observatories like JWST is stress-testing our most fundamental ideas about cosmic evolution. It is a collaborative tension that pushes both thinkers and observers to new heights, gradually untangling the glorious chaos of the universe's first chapters. That violent cosmic foundry forged the very ingredients of life itself. Every atom of carbon in your body, every breath of oxygen you take, was once stardust created in the heart of a long-dead star and scattered across the galaxy by a supernova's fury. The chaotic feedback loops, the galactic winds, and the relentless mergers were not merely shaping galaxies, they were cooking the essential elements of our existence. Without that frantic early period of star formation and death, the universe would have remained a sterile, simple place, a vast ocean of hydrogen and helium utterly incapable of forming a single planet, let alone a living cell. Consider our own Milky Way. Its specific history of collisions and steady gas accretion appears to have been just right. A more violent merger history might have torn apart a stable galactic suburb like our own. A quieter one might have left us without the rich chemical diversity needed for complex chemistry. The spiral arm we call home offers a relatively peaceful haven, shielded from the most intense radiation of the galactic core, yet periodically stirred by passing density waves that might even trigger new rounds of star formation. This introduces a deeply philosophical dimension to our story. We are here contemplating the origins of galaxies only because those galaxies evolved in a specific, turbulent way. The chaotic processes we study are not just abstract events in deep space, they are the very reason we exist to observe them. This anthropic perspective suggests that the universe's fundamental character, one of dynamic and creative turmoil, might be a necessary precondition for life. It is not a scientific explanation, but a profound realization that connects the furious origins of the cosmos directly to our ability to look up at the night sky and wonder. Our existence is intertwined with the legacy of galactic chaos, a thought that forever changes our place in the universe. Despite the revolutionary insights from our newest telescopes, the cosmic dawn remains shrouded in profound mystery. We stand at a frontier where every answered question seems to unlock three more, each more challenging than the last. Perhaps the most fundamental puzzle concerns the universe's very first stars, the mythical population 3. We have strong theoretical models describing these colossal titans, but we have never directly observed one. When did the very first of these giants ignite? How did they initially gather from pure hydrogen and helium without any dust to help them cool? Finding even a single one of these primordial behemoths would be like discovering the first fossil of a legendary creature, confirming the starting point of all cosmic structure. Then there is the breathtaking speed of supermassive black holes, the existence of quasars with billions of times the Sun's mass, seen when the universe was barely a toddler, defies our understanding of physics. How could anything accumulate so much mass so quickly? Did they form from the direct collapse of immense gas clouds, or were there previously unknown mechanisms that allowed them to feed at rates we thought were impossible? This growth spurt is a cosmic scandal that challenges the very rules we thought governed these dark engines. Another great unknown is the primary cause of galactic death. We see massive galaxies that have been quenched, their star-forming fires extinguished billions of years ago. But what is the dominant executioner? Is it the relentless output from a central black hole, blowing away the galaxy's gas? Or is it the cumulative effect of countless supernovae, reheating the fuel until it can no longer collapse? Perhaps it is the environment, the brutal stripping and harassment that occurs within crowded galaxy clusters. The evidence points to all of these, but we do not yet know which force typically delivers the final, quieting blow. The intricate dance of feedback processes adds another layer of complexity. How do the powerful winds from supernova interact with the even more colossal jets from active galactic nuclei? Do they work in concert, or do they sometimes cancel each other out? Understanding this balance is key to explaining why some galaxies, like our Milky Way, have sustained a gentle pace of star formation, while others flared brilliantly and died young. The story of reionization is also incomplete. We know the cosmic fog was burned away, but which sources provided the majority of the ionizing photons? Was it the fierce light from massive stars in countless small galaxies, or was it the brilliant, focused glare of early quasars? Pinpointing the primary architects of this universal transformation is crucial for understanding how the cosmos became transparent. Even our foundational concept of dark matter is being probed at these early times. Does its nature, whether cold, warm, or self-interacting, leave a unique fingerprint on the smallest, earliest galaxies? The population of tiny satellite galaxies we see, or fail to see, around our own Milky Way could be the key evidence that reveals dark matter's true identity. The data from the James Webb Space Telescope has not simply filled gaps. It has often revealed a universe that is more complex and mature than our best models predicted, raising more detailed and challenging questions than we ever anticipated. Each of these mysteries is not a dead end, but a fertile ground for the next generation of discovery. They ensure that the study of the chaotic early cosmos will remain one of the most vibrant and captivating pursuits in all of science, promising breakthroughs that will continue to reshape our origin story for generations to come. The universe's grandest structures were not built with patient order, but forged in a crucible of beautiful chaos. Our journey reveals a cosmos where gravity's relentless pull was only the opening act, joined by an invisible dark matter scaffold and a symphony of violent forces. We have witnessed how galactic mergers acted as cosmic demolition derbies, triggering firestorms of starbirth, while supermassive black holes awoke as brilliant but capricious regulators, capable of both creating and destroying with their immense energy. This was not a slow, stately progression. It was a frantic, messy, and deeply unpredictable drama, where chance encounters and a galaxy's specific environment shaped its destiny as much as the fundamental laws of physics. The evidence pouring in from the James Webb Space Telescope and other observatories paints a consistent picture, a universe in its infancy that was far more dynamic and productive than our calmest models ever allowed. This understanding invites us to embrace complexity, to see the inherent turmoil not as a flaw, but as the essential creative engine of the cosmos. These ancient processes, unfolding billions of years ago in a distant, frenzied nursery, were not abstract events. They were the necessary precursors that set the stage for our own existence. The heavy elements forged in those early stellar furnaces, the stable galactic disk of the Milky Way shaped by its unique merger history, the specific cosmic address that allowed our solar system to form, all of it traces back to that initial chaotic burst. The story of the early universe is far from complete. Each new observation adds a thrilling chapter to this epic tale. We would love to hear your thoughts and questions in the comments below. If you enjoyed this deep dive into cosmic origins, subscribe for more journeys to the wonders of our universe. The greatest story, the story of everything, is still being written.